Welcome to Bite-Size Data Science. In the previous video, we talked about recommendation engines and why we should use them. In this one, we're looking at an algorithm called alternating least squares. Before we get into Notebook, we need some background. Let's take the example we'll use in the notebook, movie recommendations. We have 1,681 movies and 942 users. We also have a file that contains almost 100,000 movie ratings by the users. By the way, I want to thank Ethan Rosenthal for his article and code for recommendation engines. You can find references on those and more in the description. The first step is to approximate the rating matrix as the product of a user matrix and a movie matrix. This is called singular value decomposition. Each of these matrices, U and M, have a number of factors for each user and movies. This means that if you take the factors for user 2 and multiply them by the factors from movie 3, we get the expected rating for the element of matrix M. The rating matrix is of dimension 942 by 1,681. This makes for over 1.5 million ratings. Remember, we are starting with only 100,000 ratings, which represent only 6% of the total. Let's take a moment to talk about the users and movies factors. These elements are sometimes referred as hidden factors. Each factor represents a weight for an underlying grouping. The groups are common to all users. The different weights then impact the ratings given by a specific user. We don't have names for these groups, but it does not matter. If it helps, think of them as being drama, comedy, action, and so on. How do we figure out these factors? The goal is to find the best fit that limits the error. It is similar to when we try to fit a line on a number of points in linear regression. We're ready to see how we solve our problem. Let's assume we are using 10 hidden factors. We first create the two matrices and initialize the factors with random numbers between 0 and 1. To solve the problem, we'll look at a few operations. First, we assume that the movie factors are final and we calculate each user factor. Let's look at what is happening in pseudocode. We multiply the 1,682 ratings of user U by the movie factors. This results in a vector of length 10. The left side of the solve function is a 10 by 10 matrix. We add the L 10 by 10 regularization matrix. The result is a calculated 10 factors for this user. Now this is where the alternating comes from. We do a similar processing where we assume the user factors are final and we need to calculate the movie factors. We loop over alternating setting user factors and movie factors until we reach a certain condition. The result is the two matrices that allow us to create the ratings a user would give a specific movie. Let's get into a notebook. I am using the IBM Watson Studio environment to run my notebook. If you are interested, you can find a link in the description on how to create a free account on that platform. Links to the notebook I'm using here are also available in the description. Let's skip the part where we read the data and jump right away to the singular value decomposition. We create the rating matrix and initialize the values for the ratings data frame. We then initialize the user and movie vectors with random values. We're ready to put together our alternating least square function. Refer to the articles in the description for more details. The ALS_step function is divided in two parts that do the same operation. One to calculate the user factors and the other to calculate the movie factors. Let's look at the first part. First, we pre-compute the part of the formula that will be used in the loop. The loop uses the NumPy linear algebra solve function to solve the linear equations. You should recognize the formula from what we discussed earlier. To see how ALS does, we look at a specific user and a specific movie. We then loop over the ALS steps 20 times. We can see the first hidden factor change over the iterations for both user 92 and movie 121. Finally, we see that the rating for this movie is 5.0 and that the calculation gave us a rating of 4.45. This approach to recommendation engines also has drawbacks. For example, What do you do when you want to offer a new product? You need to figure out a way to create useful data on it. This is called the cold start problem. There is a lot more to this approach. How do you decide on the number of hidden factors, number of iteration, or value for lambda? I suggest you go read Ethan Rosenthal's article to learn more about it. See you next time on Bite-Sized Data Science, and don't forget to subscribe.